Hello and welcome to my talk. I'm Julie Tourniaire, a PhD student in École Polytechnique, and this is my presentation for the Bernoulli IMS One World Symposium. In this video, I'm going to talk about the population dynamics of a species colonizing an heterogeneous environment. This work was supervised by Pascal Maillard and Gaël Raoul. First, let me begin by introducing an example. In the book Biological Invasions, Theory and Practice, Shigezada and Kawasaki mentioned this kind of patchy environment where individuals have to go through favorable and unfavorable regions to colonize the real axis. Favorable patches are regions where breeding conditions are favorable, while unfavorable patches correspond to harsh environments where the population develops slowly. This may be due to mountains, roads, oceans, and so on. To describe this kind of situations, we consider systems of interacting particles in which the duplication rate of the individuals is space-dependent. We can even think of time-space dependent rates. For instance, this might be useful to describe the effects of global warming on a habitat. Besides, we assume that the individuals undergo local competition and that they migrate independently after the birth. The goal is then to study the invasion speed of such a population and to compare it to the deterministic model obtained with the large population approximation. More precisely, we consider discrete time and space variables, k delta t and I delta x, and three parameters: epsilon, the scale of heterogeneity of the environment, the time-space duplication rate, r, which is assumed to be a smooth function, and capital K, the typical size of the population on a site. At time k delta t, the configuration of the population is given by the infinite vector nk, and we denote by xk the position of the rightmost particle in the system at generation k. Xk then corresponds to the position of the invasion front. In this model, we move from a generation to the next one, applying three steps: reproduction, competition, and migration. So we start by describing the reproduction step. At time k delta t, each individual living on the site I delta x duplicates with probability given by the rate function at the current location and time, scaled by epsilon and multiplied by delta t. Then, all these new particles replace the ones from the previous generation and undergo the competition step. During the competition step, on each site, the population size is truncated at capital K. Finally, all the surviving particles migrate independently following mu delta x delta t, which corresponds to a discretized Gaussian distribution. The resulting configuration constitutes nk plus 1. Under these assumptions, we obtain the following theorem. If R is smooth and bounded from below by a positive constant, then for all delta positive and for all delta t delta x small enough, depending on delta, we can find a k star depending only on delta, delta t and delta x, such that for all k larger than k star, the probability that the distance between the rescale process and the solution of the ODE C is smaller than delta for all generations from 0 until approximately logarithm of capital K tends to 1 as epsilon tends to 0. Roughly speaking, we get that for K large but fixed, the process tends to the solution of the Cauchy problem C as epsilon tends to 0. Another approach of this problem would be to first let k tend to infinity. In this case, one can show that the model converges to the solution of the Fisher-KPP equation 1, u epsilon. Second, we would let epsilon tend to 0 and prove that u epsilon tends to the viscosity solution of an Hamilton-Jacobi equation. Through this approach, in the case of the patchy environment, Shigesada and Kawasaki proved that for narrow patches, the speed of invasion of our system is approximately c, which is square root of 2 times the harmonic mean of R. Therefore, let us plot on the same graph the rescale process, the solution u epsilon of the Fisher-KPP equation, and the solution of the ODE given in the theorem to find which one constitutes a suitable estimate of the process. We start with capital K equal to 20 and epsilon equal to 0.1. The blue line corresponds to the finite difference approximation of the solution u epsilon of the FKPP equation. The orange line corresponds to the exact solution of the ODE. We see that the rescale process, which is the green line, lies between the blue and the orange lines. And if we let capital K increase with epsilon fixed, we see that the green line gets closer and closer to the blue line. Conversely, if we go back to the case capital K equal to 20, epsilon equal to 0.1, and if we let epsilon tend to 0 with capital K fixed, we see that the rescale process tends to approximate the orange line. Therefore, there are two regimes. If epsilon is large compared to 1 over k, then the rescale process converges to the deterministic model, that is the solution of the FKPP equation. If epsilon is small compared to 1 over k, the rescale process tends to the solution of the ODE C given in our theorem. So as a conclusion, our approach allows to study biological populations whose sizes are small compared to the heterogeneities they have to go through. For instance, it enables to take into account the effects of mountains, oceans, or even global warming on the population dynamics. So this is the end of my presentation. Thank you for watching my video.